Hi folks, welcome back to AP Statistics. This is Mr. Robeson. Today we're looking at confidence intervals for paired mean. All right, so we'll have data that's paired together somehow. What does that mean? Well, let's take a look. So paired data is when two values of the same quantitative variable, so for the same variable, for each individual or for pairs with similar characteristics, so similar individuals. So remember when we did match pairs designed back when we did experiment design? That's basically what's happening in here. So match pairs. All right, so either each person does the same experiment twice. Like usually when we do this, we go outside and we throw pool noodles and we see how far they can go with throwing with your right hand versus throwing with your left hand. We could do the same thing with throwing like a baseball or a football, but then each person would be assigned to do each treatment. And usually we randomly decide which one they do first. So if a person's doing both treatments, an easy way to do that, to randomly assign them to do one first and then the other second, would be a coin flip. All right. Also, if we're doing studies involving twins, if we have one twin do thing A, one twin do thing B and compare, that would also work. Right hand versus left hand, like I already mentioned with throwing things, things involving the same individual twice. So we also have another test where we read words written in different font colors, and the words are all colors. So you could read the actual colors that are there, the written colors, or you can read the color of the words. We usually do that in class, but again, we don't really have the option to do that. Another example here is like if you have brothers and sisters, you can test like the brother versus the sister, or two brothers versus each other or something. Husbands versus wives. Again, they're all similar to each other because they should all live in the same area and that sort of stuff. All right, let's see. So with paired data, we need to find the difference between each pair. All right, so we're not finding like the mean of all the brothers and the mean of all the sisters and then comparing. We're finding the difference between the brothers and sisters and then comparing those differences. That's what's different here. All right, and it's not the same thing. It does not work out to the same distribution. The mean will be the same, but the standard deviation will be different. And that's key. We get a much smaller standard deviation when we do this match paired, which gives us a better estimate. All right, and it only works if we're doing match paired. We can't do this if we're not matching pairs together specifically. All right, so here's an example. A psychologist wants to determine if living in a high income versus a low income family affects IQ scores. Researchers find 12 identical twins, what are the chances of that, who were separated at birth. Crazy. One living with a high income family, the other living with a low income family. I think this is made up. Find the mean and standard deviation of the data. So we have IQ scores for the high income twins versus IQ scores for the low income twins. And we want the difference, A minus B. All right. Compare the combination of distributions to standard deviations. All right, we can actually compare both. And what I'm going to do is, well, we can actually subtract all these differences and say, okay, that's 8, that's 5, that's 9, that's 6, that's 5, and so on, and keep doing all that. But we could actually get our calculator to do this for us too. And we're lazy, right? So, not too lazy, but we're a little bit lazy. So if we go to our calculator, and I've already got the data put into my calculator here for L3 and L4. So the top one here is L3. The bottom row here is L4. So if we want to find the difference real quick, we just make this next list L3 minus L4. Enter. And there, it did all the subtractions for me. And it looks like I messed up on a couple numbers because it looks like some of them are well over 100. So let's see if I can fix those. Let's see. So I was typing these in by hand. And what was after 104? 114. So I left out an extra 1 there. 114. Easy fix. Done. And the one after that was also 114. 114. Enter. Oh, that's an extra one. Yeah, I guess you can see how errors happen here. It's good to look at the numbers just to check. So on the other side, we definitely didn't have anybody with an IQ of 10. That was 100. It doesn't like it when I hit the 0 twice. I think that's the problem. All right, and now let's go and we'll try this again. No, it doesn't want to automatically calculate. Second L3 minus second L4. And there we go. Now none of the numbers are in the hundreds over here, so it looks like we're doing okay. Yeah, there is that one of them that's negative, and that's okay. Yep, we got that one of them that's negative. Not the end of the world. All right, so now we want to look at the difference. So let's just go to stat, and we're going to calculate the one variable stats for, let's just do L4. Actually, no, let's start with L3. Right, it was L3 and L4 where the two lists were. Our frequency would be 1. What did we do? Frequency list. We don't need a frequency list. There we go. There we go. And let's see, X bar is 109.5, and the standard deviation, this is a sample, is 9.47. So for the mean for A and the standard deviation for A are 109.5. That's the average IQ score for the first sample, and 9.47. All right, now let's take a look at the mean for B and the standard deviation for B. So let's see, stat, calculate one variable statistics. And now we're going to look at L4. And we've got a mean of 105.3, repeating, and a standard deviation of our sample of 8.55. So if we did the wrong thing, and this is the wrong thing here that I'm going to do, for unpaired, we would say that our standard error, I guess we'll use SE of X bar A minus X bar B, would be the square root of, let's see, so this standard deviation, 9.47 squared over 10 plus 8.55 squared over 10, and we would calculate that. So let's do that. Second, square root of 9.47 squared divided by 10 plus 8.55 squared divided by 10. And give us a standard error of 4.0. All right, or the other thing we could do is we could say that the standard deviation for just the difference, I guess S of X A bar minus X bar B, would be the square root of 9.47 squared plus 8.55 squared. And we can look at that and see what that is. But again, this is not necessarily the right thing to do here. So the second square root of 9.47 squared plus 8.55 squared. Oh, I left off a 5 there. 5 squared. There we go. 12.75. All right, but we have paired data, so we can actually get this to be smaller than this, and our sampling standard error here would actually be smaller than that as well. So what ends up happening here is we look at this, the standard deviation of the difference. So we look at the X bar difference, DIFF. All right, and we want the standard deviation of that. All right, so if we do that on our calculator, that'd be, again, a one variable stat. But now we're using the difference, which we put in L5, which gives us a standard deviation of 6.53. All right, so that's the standard deviation of the difference. And I suppose I should write this as A minus B, standard deviation sub A minus B, which notice is much smaller than this standard deviation. It's almost half of it. And if we wanted to look at the standard error of the A minus B stuff, well, we would have this standard deviation, 6.53, divided by the square root of 10, because we'd be treating it as just one distribution and not two distributions. All right, so we would type in the 6.53 divided by the square root of our sample size, which is 10, and that gives us 2.06. 2.06, which compares to this is much, much smaller. All right, so the smaller one gives us a smaller interval in the end, which is what we want. All right, so when we're doing this, again, instead of defining both means, we just say the mean difference, and it's the true mean difference of, and we say what the two things we are subtracting are. We state our confidence level, we state our known statistics. Oftentimes we're using data. We're doing a paired t-interval for mean difference. All right, so that is the name. It's a little different. It's paired. So it's not really treated as two sample. It's treated as a paired sample. It's kind of two samples, but it's really one sample. I don't know. It's a little different. All right, so we're working with a t-interval. Oftentimes we're going to use data. All right, and we'll have to make that third list. All right, the conditions are just about the same. So either we need a random sample or we need a randomized experiment. So this is new. As long as our sample doesn't have to be random, as long as we have something to randomize the order, say like the coin flip to see which thing you do first, if it's the same person doing two things, that randomization is done with the coin flip or some other sort of randomization method. The normal sampling distribution is all the same stuff as before, the normal population or n's greater than 30 by CLT, or we look at the graph. All right, independence, same condition there. All right, and if we're doing this, really we do this just like if this were a one sample interval. That's why we're doing it as the t-interval, and the one sample is the difference. It's that third list we make. All right, and our conclusion is still the same thing, except we're saying now the true mean difference in context. All right, so back to these guys. So we already looked at this a little bit. So our mean difference, I like to use capital D for whatever reason, is the true mean difference in IQ scores of twins in high income minus low income families. There we go. I was going to say houses. There we go. Families. All right, so that's sometimes kind of long, but that's okay. Our confidence level is we want to make a 95% confidence interval. So 95%. All right, and it looks like we definitely have the data here, so we're not going to be able to write much down. Besides that, our sample size is, in fact, 10. All right, this is paired data because we're looking at twins that are separated, so these two twins go together. They are paired. Each one of this that's a twin, those are two twins, those are two twins, and so on. So this is a paired t interval. Oh, I crossed my L here. Interval for, that's what I was thinking there, F, mean difference, the difference of means. All right. They were, as far as we know, they were randomly assigned. All right, so it's not random sample, it's randomly assignment, or random assignment. All right, as long as some sort of random comes into play, that gets us an unbiased estimator. That works. For this, we're probably going to have to look at the graph. I believe I did the graph once before. It is a little bit on the skewed side, but it's not horrible. It does work out. So the graph is no outliers and not strongly skewed. So those check out. So we have an approximately normal sampling distribution. All right, if we look at the independence one, all right, our N here is 10, which is definitely less than 10% of all twins. Maybe not less than 10% of all twins that are separated at birth, but definitely less than 10% of all twins. We're doing a t interval in our calculator. So let's check that out. So let's see. Second, no, I don't need second. Stat, test, t interval was number 8. And the list that we want to use, so we're going to use data. Actually, we have the stats from last time, but we're going to use data. And our list was the difference. So the difference was an L5. So you might have to do some work first to get that difference. And we're doing a 95% confidence interval, so 0.95. And what do we get as an answer here? All right, so 0.015, I guess that would round to 8.32. Guess that'll work. And let's see, what else do we want to write down? X bar, S, and N. All right, all those would be good things to write down. So 4.167 X bar, and this is the X bar of the difference, is 4.167. S of the difference was the 6.5. Was it 6.53? Yep. All right. And then we write our sentence. So we are 95% confident that the interval from 0.015 IQ points to 8.32 IQ points captures the true mean difference. Basically, I'm writing this again. In IQ scores of twins in high income versus low income, or we could say minus low income, that's fine, income families. Whew, that was long. All right, here's another example for you to try at home. Again, I'm just asking you to find the confidence interval. So just quick recap, we'd have to put one of these in L1, one of these in L2. All right, find an L3, which would equal the difference in the two. It looks like the bigger numbers for the most part are in L1. So it would be L1 minus L2 is what I'd probably want to do. And then on L3, we would do the T interval. So we'd use data, we use L3, and we would do 90%. All right, I'm not going to write that out, but if you want to pause it here and take the time to do that and see what the differences are between doing the test with music versus doing the test without music. Looks like music was helpful to a lot of these people, strangely enough. All right, and let's see, how are they paired? Match paired experiment music helps hinder math performance are listed below. At times it took students to complete a 50-question arithmetic test are listed below. Students were randomly assigned which setting to test in first and assumed test times are normally distributed. All right, so we got to, I guess everybody tested twice. So they did 2 different arithmetic tests, and they randomly assigned which one did first. So that random assignment takes care of that. All right, so if you want to type this into your calculator, go ahead and do that. The answer you should get for your confidence interval is 2.27 to 8.90 is the difference. All right, so there is confidence intervals for paired data, and that is the end of 9.2. So check out the homework on Google Classroom.